So the object was, instead of talking about everything available, I just specialize in one kind of object or two kinds of objects. Um, every once in a while, I'll do a thing like um, sometimes it's more illuminating to observe just one kind of object instead of jumping all around with galaxies and clusters and you know, I'll just go out and say, you know what, I'm only going to look at globular clusters tonight, or I'm only going to look at open clusters. And of course, that depends on the season. But I find it illuminating if I'm just looking at one particular kind of cluster. I go around and I look at one and I look at the next one, and then I can kind of compare, maybe go back to the original. And I found that's really helpful in building my mental collection of what I'm looking at. And if you're just looking at globulars, after a while, it's like, oh yeah, look at the differences. So um, that's where the idea comes from, that it's worth just specializing in one particular thing. Um, I love this William Herschel quote. And the thing is, you don't just put your eye up to a telescope, you have to practice learning to see. And some of you have seen my talk on learning to see, and different things you can do to make what you see in the eyepiece, to learn how to see it more carefully. So a theory is an idea that is suggested or presented as possibly true, but that is not known or proven to be true. I have a new theory. What is my theory? That it is? You may well ask me, what is my theory? Well, that is the theory of mine. Well, this is what it is. My theory that I have, that is to say, which is mine, is my theory. Oh, what is my theory? My theory that belongs to me is as follows. That's Monty Python. Um, I thought I could do an interesting talk about learning words and terms to use in describing globular clusters and open clusters. And part of the thing in my talk about learning to see generally is to have certain things you look for, a checklist. Is that round? Is that oblong? Is it, there's a lot of words you can use. So I thought in my theory of this that I would come up with a bunch of words that if you had them in your head, it would help you look more carefully at objects. And part of that came from this book by Christian Lugenbuehl and Brian Skiff. I bought this book 40 years ago, and it was mind changing. And it's very technical, but it's like no other observing book. So here's what they do, the two of them using different telescopes. They talk about the object, its the dimensions and diameter and its visual magnitude and so on. So I won't read this to you, but it talks about what the object is. And then, for instance, they say 6 centimeter, meaning a 60 millimeter scope, is there's the stuff that you can read. And it's very technical. And in this particular case, it's sort of, if you really wanted to see Messier 17 better than you ever had, you would print this out and bring it with you. But notice they don't bother with any photographs, it's all descriptions. And that was illuminating, and I became a better observer because of that. Here's another object. Words like diffuse and poorly concentrated, slightly brighter. I've never seen central pip. The other yellow thing halfway down, the cluster is not condensed. So I thought if I came up with a whole bunch of words that, I could introduce you to, it would help look better because you could see better or something. Well, that theory was faulty. There were so many different words, and they kind of weren't. Yeah, I'll talk about this a little bit later, but it didn't work out the way I thought it was going to. So the theory, which was mine, which I forgot how Monty Python said it, but anyhow, was a faulty theory. So observing star clusters. This is just a brief introduction. It's not a really good survey of it. Star clusters contain some of the oldest and youngest stars in our galaxy. They represent the beginning, the present, and the future of the universe, from the tiniest, sparse, open clusters with only a dozen stars to the giant globular clusters replete with 1 million stars. Observationally, clusters are the most appealing deep sky objects. And this is a globular cluster done by Adam Block at the Mount Lemmon Sky Center. I forgot how big his instrument is, but it's sort of a professional observatory. He may be using a 24-inch scope. And this is the Pleiades, obviously taken with a professional instrument because it has the veins, the stars from the veins. Even in urban and suburban locations with light pollution and dubious weather, many star clusters are much easier to observe and image than other deep sky objects, such as galaxies and nebula, due to their stellar non-nebulous nature. So the sense being, at least you'll see little star points of light if you don't have clear dark skies. So this is the double cluster, and whenever I'm out, and if it's the right season in Orient or Vermont or out west, this will be the first object that I start with. It is so spectacular because there's two condensations. It is a joy to see. From my side yard, it looks like that, and that's not impressive at all. I mean, I look at it because it's there, but then when I get to Stellafane and see that, it's like, holy cow, that's, you know, I always end the night with looking at that again. Somehow it's inspirational or something. One note here that I have, if I'm showing the sky to people and you put the double cluster in the center of the field, when people look in, they go, wow, look at all the stars. So I do a thing where I put it in the center of the field and then I push the telescope a little bit until the object goes out of the field. And you don't see what you see here. You probably see 1/10 the amount of minor stars. So you see a black sky and some stars. And then I tell the person, just pull the telescope to the left a little bit. And this comes into view, and it's almost theatrical. I mean, it is just striking to go from a field where there's, you know, a bunch of faint stars to this. It's really dramatic. And you'll see that I'm mixing up all kinds of things all at the same time. So it's important to take your time while observing. It's not a race, and there are no medals for the person who can see the most objects in one sitting. Instead, it is better to savor each cluster and spend some time getting to know it. When you believe your telescope is in the correct place, but you are struggling to see anything, or you cannot discern any detail in an observed cluster, you can try the following methods. Applying slight movement or tapping the telescope or jiggling it can cause some invisible objects to suddenly pop into view, or previously unseen detail can suddenly become apparent. This is because our eyes seem to respond better to moving objects rather than stationary ones in low light environments. I guess that goes back to looking out for tigers jumping out of the grass in the middle of the night. Looking at a telescope target directly is comfortable and natural, but the central section of the eye is the least effective part in low light conditions. Averted vision can aid in detecting faint detail, and it involves looking off to one side using your peripheral vision. So let's say I have I don't know, a faint globular cluster. Instead of looking right at you, and I usually use this with nebulosity, but instead of looking right at it, I look to the, let's say, the right of it, and then I go around the object, never looking right at it, but looking at what I'm looking at straight ahead, but the object is to one side, and then I go up and over and around and underneath. And you would be surprised at the extra detail you will pick up in nebulosity and other faint things because of the averted vision. Binoculars are a useful tool for scouting clusters as they are light, easy to use, and completely intuitive when locating an object. A binocular review represents objects exactly as they appear in real life. Reflectors invert the image so it appears upside down, but this is not of major concern as you can simply rotate your star chart to match the view in the eyepiece. The tricky one is a refractor with a diagonal on it because it flips the image left to right, providing a mirror image, which is more confusing. I've had that looking at the moon with craters, and when you have a mirror image, it's very confusing, I'm finding, to sort of get sorted where you are and where the object is you want to find. The drift method can be used to this has to do with calculating your the telescope field of view depending on the eyepiece. And there are mathematical methods you can use, but I kind of like this. To calculate the field diameter of a particular eyepiece, determine the length of time it takes for an object to traverse the telescopic view and multiply it by 15. So, let's say you have a globular, put the brightest part of it just outside the field of view, and then wait, and it will come into the field of view. Start your stopwatch, wait for it to traverse the field of view, and then multiply it by 15. If a cluster takes 5 minutes to traverse the field of view, times 15 gives 75 arc minutes, or 1.25 degrees. And knowing field diameter is helpful if you're trying to figure out what some object sizes are. This goes beyond casual observing. Maybe you just have a notebook and make a little note about a particular object and how large it seems to be. So there is a thing here that I gotta find. I've got some stuff about star birth, but we probably don't need that. I'll mention stellar types. Our galaxy, the Milky Way, contains two distinctive star populations, known rather appropriately as population 1 and population 2 stars. These two types are characterized by their differing ages and chemical content. Population 1 stars are typically young, hot stars that began life within the last few billion years and are still forming today. Concentrated within the spiral arms of the galaxy, population 1 star orbits are inclined to the plane of the galactic disk. Population 2 stars are much older, typically 10 to 15 billion years old, so they comprise some of the oldest stars in the galaxy. located primarily in the central bulge and also in the galactic halo that surrounds the galaxy. Population 2 stars form the basis for the majority of globular clusters. Their orbits are erratic and they traverse the galaxy on an elliptical path. So there are over 1,100 known open clusters in our galaxy, but the true total may be up to 10 times higher than that. The Milky Way has more than 150. I said 1,100 open clusters. That's what I meant to say. But the true total may be up to 10 times higher. The Milky Way has more than 150 known globulars, and there may be many more. My sense is there's a lot more variation in appearance of open clusters than there are in globular clusters. Let's see. On a clear moonless night, you can see a dozen or so open clusters with the naked eye. These stellar groupings are sprinkled against the myriad of background stars and have been known since antiquity. Not until you observe these objects with a telescope or binoculars is their true beauty revealed. Contained within these associations is anywhere from a dozen to several thousand stars of different masses, but with the same age, distance, and chemical properties or stellar type. There are about 1,600 confirmed open clusters or cluster candidates in the Milky Way, ranging from bright, loose examples, remember those words, bright, loose, with nebulosity like the Pleiades in Taurus, to older and more compact clusters, such as the Wild Duck cluster visible in Scutum. Most open clusters reside within the spiral arms of the galaxy and are generally composed of young, hot stars. They are loosely associated with groupings of physically attracted stars bound together by gravity. Gas and dust is commonly found within these clusters, and many are surrounded with nebulosity left over from starbirth within the clusters. All the stars in an open cluster orbit around one another and are affected by each other's gravity. Well-known open clusters include the Beehive cluster, or Praesepe in Canada, the Hyades in Taurus, and the Jewel Box. Oh, forget that. That's in the southern hemisphere. There are a classification system. It's called the Trumpler system, and it has three main sections. And you will not be tested on this, but it gives a clue as to what to look for. Central concentration of clusters, and they say open clusters, but it sounds more like globulars. They use Roman numerals 1 to 5, which donates decreasing contrast in relation to the star field. So 1 is detached and strong central concentration. 2 is detached and little central concentration. 3 detached and no central concentration, and then merges into the field. Then there's a brightness from 1 to 3, and there's a richness, and they use letters for this. 50 stars or less is a P, 50 to 100 is an M, and 100 stars is an R. You know, if you had this at your eyepiece, it might be useful to you. So, observing open clusters and associations. Open clusters can be observed all year round, but are especially prominent in winter skies, with some of the brightest examples on show, such as the Pleiades and the Hyades in Taurus. During winter, there are many other excellent open clusters visible in several constellations, including Gemini, Auriga, Monoceros, Cassiopeia, and Puppis. In the clear skies of summer, open clusters are also plentiful in Sagittarius, Scutum, Cygnus, and Vulpecula, to name a few. Open clusters can also be observed during the spring and autumn. Open clusters tend to be spread over a large area and require a wide field and low magnification to completely be contained within the telescopic view. Using a high power eyepiece will simply over enlarge the cluster and you will not see it in its true glory. And I would say you wouldn't see it in context. What's around it? A long focal length telescope, higher than f6, can produce a similar result. So a fast, short focal ratio is preferable for these clusters. Binoculars are also an excellent choice, especially the more luminous groups. Several, in fact, look better in binoculars than a telescope of any size, and that would be, of course, the Pleiades. So this is one of my homemade telescopes. It's a 6-inch f6, and it's called a richest field telescope. I built this in a thing that doesn't even look like this. It was a portable scope that unfolded to take a trip to Australia. So I made the mirror and made this scope that I carried on the airplane. It was in a bag that was 2 feet long and 6 inches high and 2.5 inches wide. And I used it in Australia because it was small and lightweight. I used it on a photographic tripod. And when I came home, I built this. And when I got it done, I didn't use any other telescope for 6 months. I had never explored the sky in what's called a richest field telescope. So that's the 6-inch f4. And this is an 8-inch f4, a little bit different design. It's designed to be broken down. There are 2 1-inch square pieces of aluminum tubing. You can see them. There's a black area in the center, the shadow inside it, but there's a slightly lighter black to the left and right. So the whole thing that the black part of it, which is cloth, is supported by just those 2 pieces of 1-inch tubing. So that's an 8-inch f4. These are the eyepieces I use for most all of my observing, and most with every telescope I own. I know there's calculations where you can, figure out which eyepieces you should buy for your scope depending on focal length or whatever. This works for me. The 22 panoptic is a wide field optic. I think it's 68 degrees. The 13 Nagler is 89 degrees, and the 7 Nagler is 89. The logic here is the 22 is about, unless you start buying big 2-inch optics, eyepieces, 22 is about as wide as you can go. It's wider than a 26. And then the next one is half that. If you're not a mathematician, 13 is half of 22, more or less. So I always start with the widest field, the panoptic. That's sort of my finder eyepiece, and I study the object. And then I take that out and put the 13 Nagler in, and that brings me closer. And I will always get a different sense of the object by doubling the magnification. And after spending some time with that, half of 13, if you're not a mathematician, is 7. The thing that I keep thinking about is M8 and M20, which are gaseous nebulae. that I look at when I'm out east or up at Stellafane. And it's amazing how the objects change depending on the magnification that you use to look at them. And once again, context is important. The 22 is wide enough that it shows the object, but it also shows a lot of what's around it. Um, so these are relatively low. This isn't as good as a Tasco because those 60 millimeter Tascos were 400 power. And here I am with 37, 63, and 116X. I keep this is calculated for older eyepieces or some of the older ones. But I keep this handy. This is on the 8-inch f4. So I know I'm looking at a 2-degree field, or with the 12 Nagler, now it's a 13, it's 1.2 degrees, the 7 Nagler, 42 minutes. And so if you're spending time really carefully looking, it helps to know what the size is. Maybe you're going to write it down. I don't know. Maybe you want to compare it to other objects. Let's say you're comparing M13 or M22 to M4 or M80, which are two globular clusters in Scorpius. So it helps to calculate, and I read you that formula, but it's nice to know how large your field of view is. This was the book that I used, that I'm reading. I'm not reading from the book, but I'm reading pages from the book. And I thought it was a really good guide and offered a lot of worthwhile suggestions for observing star clusters. I don't know if I need to. There's a section on stars, but I think I'm going to leave that out. So observing, whoa, I did this backwards, sorry. Don't go away. Oh, I guess I did. Did I do? Okay, observing open clusters. That's the stuff I just read. Sorry, it was out of order. So this was such an interesting experience. My daughter came home from college one summer and she said, "Hey, Dad, let's learn the constellations." And I'd always been interested in astronomy, but thought I can't do astronomy unless I own a telescope. So I bought a book and we went out and started learning the constellations. And we had a nice summer together doing that. And when she went back to school, I bought a 4-inch Meade Schmidt Cassegrain. And I remember I drove to Brooklyn to some crazy store under the Verrazano Bridge because they supposedly had a blem and it was, I don't know, $500. And I thought, boy, what if I get bored looking through this thing? Anyhow, as you know by now, I never got bored. Um, One of the first objects that I was looking at, and I had Night Watch, and I've forgotten what the other book was, um, were 3 open clusters in Auriga, Messier 37, 36, and 38. In one of the books, and I don't remember which one, it talked about these 3 open clusters, and it said that M37 was one of the finest open clusters in the night sky. And the book said that the stars in M37 were of lower magnitude, but there were a lot more of them. So it was a very fine, very delicate cluster. And then it said M36 had fewer brighter stars, and so it was more coarse, the term they used. And M38 was a combination of the both of them. And that was like, oh, wow, how cool is that? And here's three of them together where you only have to move your telescope one or two field diameters. And I spent a lot of time. I appreciated the suggestion, but I spent a lot of time going back and forth between them. Um, there's a book that I'll show you where these drawings come from. And one of the things that I discovered early on and read about was photographs of these objects are only a distant cousin to what the objects look like visually. I think there's a thing, for instance, with M13, something as an example, and I think I saw it, is the bright stars register right away, but the longer you expose it, the fainter stars grow larger. And so the M13 looks completely symmetrical. But I promise you, when you look at it carefully through a telescope, it's not symmetrical at all. There's some dark lanes, there's some areas with an absence of stars, there's strings of stars. But anyhow, for this example, so there's M37, and as promised, there's 36 with the coarser stars. I mean, this is such a great example for, what you can look at. And then this was the one that included both Messier 38. And I spent a lot of time. Yes.
Yeah. So, question: how would you go about? Maybe you wouldn't know. Somebody would know. How would you photograph it so it would look like you were looking at it through a telescope? Or is there a way to do that? I guess
I'm
keep it
I'm
short.
I'm going to say there is no way, which is why people do drawings and why I tend to use drawings for my examples, because the artist has seen it this way and it's going to look like this to us, and it's the nature of photography that changes things. And I think it's that business of their longer exposures so the fainter stars get brighter. I wish I could give you more information, but I think that's empirical data on my part. Um, so here are a bunch of open clusters in my favorite part of the sky at my favorite time of year. And I'm going to call it the Sagittarius star cloud, but it goes up to Scutum and so on. I'm going to talk about M22, which is to the left of the teapot. I hope you can see that. Or I should start in the upper left-hand corner with M11, the wild duck cluster, M16, M17, 18. M22 is stunning. They say that M13 is the best globulars in the sky, unless you're talking about Omega Centauri. But M22 is a rival of M13. And then going to the right to M7 and 6. When I'm at Stellafane and I start observing, I like to start with M7, and one is bigger than the other. I'll show you examples. And then I just turn left and head up. Of course, we're talking only globulars and open clusters tonight, but I go up to M8 and M20 and then over to 22 and work my way up 18, 17, 16, 11. And then, of course, over to Scorpius. I'm going to talk about it, M107 and M80 and M4. So this is M11, and this is a really good example of the photographs not looking anything like this. It's called the wild duck cluster, and it says that you will see what appears to be a flock of ducks, and I'm not seeing it here, but when you look, it tends to be sort of wedge shaped. So this is the drawing. Oh, All right, so this is M16. This is the Eagle Nebula. And this is the Omega Nebula. And it looks like, sort of, if you start at the left, there's nebulosity in this that's not as obvious to the eyepiece, maybe with a smaller aperture scope. But if you started to the top left where there's graphite on the paper, you would draw the number 2, and then you would go straight out. You would extend the flat bottom of it halfway across the field. So they show this full, but in my experience using an 8-inch telescope, it's like the number 2 with a long bottom on the line. And they also call it a check mark. This is M7, which is more dramatic than its nearby neighbor M6, and it's right under the spout of the teapot. I hope I have this right. I think 6 is the lesser one. Doesn't look that way, does it? I forget, I'm sorry. So here we go, unistellar, M11. So this looks like sort of a clump. I don't think it has that V shape in it. This tends to be more accurate. The group of ducks is flying to the right. Once again, this is a drawing, but notice how different it is. I guess there's a V in it, although it appears to be heading toward the top of the frame. But I really am a huge fan of making drawings because it more closely represents the object. And this is M11 from a larger telescope, and there's no sense of that V shape, I don't think. But the whole point is, I don't see the V shape there, but it's there in the eyepiece. This is the best example of that. And also this makes my point that we're seeing it at too high a power. A scientist or somebody might want to have this much power so they can count the stars, but it's far more beautiful when you back away from it. I talked about this already, the classification systems that we mentioned. I'm just trying to think here. Is there something that I left out in my jumble of papers? He says here, color is generally more evident when using direct vision, whereas subtle detail is more apparent through averted vision. I need to start looking more carefully because in 6 and 8-inch scopes, I don't believe I have ever seen color that I can think of. But, maybe if you have an 18-inch or something, you'll see it. They say, he talks about a notebook. Any other details that you noticed while observing are important and should be recorded, such as the differences in color and brightness of the component stars and any obvious patterns. And what's interesting, they say the Trumpler system, modern open cluster classification, but the first central concentration is certainly a major part of globular clusters. So here is this magnificent photograph of M13. I think it was a 24-inch scope that's in the observatory at the Sky Center. I mean, that is stunning. And of course, the first thing you think of is, why don't they all crash together? Are they not smashing into each other? And the answer, which is completely unintuitive, is there's so much space around each star, there's no chance it's going to smash into another one. And they're all in elliptical orbits. It's like a beehive. So this is the example of what you get from a telescope and a long exposure. This is John Herschel's drawing And I don't remember the year because I don't remember any history, but notice that it's uneven. It's not symmetrical. It has some dark voids coming in from the top, the left side. There's fewer stars on the left side of the central concentration. Nothing like that's visible here. Well, maybe to the left, there's at the 9 o'clock position. Maybe it's not entirely symmetrical, but anyhow, these are absolutely wonderful. So here's Ross, Lord Ross, and his giant telescope made out of blocks of brownstone or something. And there's that Y shape in there. And there are also strings of stars that are spoken of in the Luginbühl book that I showed you early on. You wouldn't recognize this as M13 if it wasn't labeled, but it gives you some clues of what to look for. So as it rises, these are things you can look for. Oh, I went the wrong way, sorry. And this is Trouvelot, who was one of the most astounding artists. He came over from France and he was interested in astronomy and somehow talked himself into the use of the great Harvard refractor. And this is the way he drew M13. So all of these would be useful the next time you look at it and try and say, gee, are there voids? Are there strings extending out? And in my experience, there are. So it says here, of all the deep sky phenomena, globular clusters must be one of the most striking objects visible to amateur astronomers. With their vast spherical orbs lie tens of thousands of ancient stars, tightly packed like a scintillating mass of insects. Remarkably, there are just over 150 confirmed globular clusters in our galaxy, which seems an incredibly small number compared to the size of the galactic halo and the number of open clusters. Globular clusters define the outer area of the Milky Way. They trace out its original extent from when the galaxy formed. They are extremely old, generally massive in size and star numbers, and are distributed fairly uniformly in a spherical inclination around our galaxy. Stellar numbers are as diverse as the clusters themselves and can range from tens to hundreds to thousands of stars, with 100,000 to 1,000,000 stars being typical. All globular clusters live within the halo, which is the least understood part of the Milky Way, and follow an elliptical orbit around the galactic center. Globulars are fairly symmetrical systems and generally tightly packed toward their core or nucleus, gradually fading out to smaller star numbers in their outer regions. They are almost always linear in nature and spherical in shape. I don't know what he means by linear in nature, but certainly they're spherical. In the northern hemisphere, M13 in Hercules is the brightest, most accessible object. Many globular clusters do initially appear similar, but in reality, their size and brightness vary dramatically by a factor of almost 100 from the smallest to the largest. How did they form? Globular clusters were created from the primary nebulous gas soon after the formation of the Milky Way. As these gas clouds compress, their mass becomes denser and begins to cool down. Eventually, it begins to collect into massive clouds called giant molecular clouds, and gravity compresses the material further still. After about 100,000 years, the first massive stars are born. Pressure and radiation then disperse. Pressure and radiation then disperse from the cloud, leaving the newly formed globular cluster behind. Here's globular size. The most distant clusters are generally the largest, as they are less affected by tidal forces trying to pull away star cluster members. A typical diameter for a globular is 50 parsecs, or about 160 light years in diameter, but they can be anywhere from several tens to hundreds of light years across. The stars in an average globular are packed in at about 1 star per cubic light year. And it's like, you're kidding me, right? They look like they're right next to one another. Most globulars are at least 10 times larger than typical open clusters. So 10 times larger than typical open clusters. But as they are generally 10 times further away, globulars can appear similar to open clusters from a visual perspective. Globular clusters are stunning objects from a visual observing perspective and are arguably one of the best deep sky objects for amateur astronomers. I don't know. I think that a lot of the nebulae are far more complex and more interesting, but that's what the guy says, and are arguably one of the best deep sky targets. Some globulars are visible with binoculars, for example, M13 in Hercules, which appears as a fuzzy star and is in the northern hemisphere's finest example. I mentioned M22. The best time to view these spherical giants is during the summer when the Milky Way does not obscure the view. Ophiuchus is a constellation replete with globular clusters, and they can also be found in Serpens, Hercules, and Sagittarius. In autumn and winter, they are few in number as we are looking toward the wrong part of the galaxy, which is why I'm giving my talk when I am. Globulars vary quite considerably in star content and density, such as the bright, loose globular, remember those words, in 107 in Ophiuchus. Rich, compact globulars like M2 in Aquarius require higher magnification and larger apertures to even begin to resolve the clusters to their stellar cores. There used to be a Shapley system of classification, but that's been replaced by Crumpler. A surprising amount of detail can be detected at high powers, and many globulars show evidence of texture and shapes, clumping of stars, and mottled structure. I should also add when I was, and here's another drawing of M13. This is interesting, right? We go back to this, and there's that triangle thing, or the paths. And I didn't notice this, but that's visible as a dark lane in this view of the globular. So I think for most of us, we've always thought of M13 as being perfectly symmetrical, and guess what? It's not. So this is kind of fun. Both of these are in Scorpius, M4 and M80, and look at the difference in qualities. These are drawings. M4 is so much larger than M80, and this gives a nice example of the range of some of these. So here's M80 and M4. M4 is on the left, and this is a drawing of M4, and they include a lot more of the surrounding. And I guess they've drawn them at different scales because this is clearly, or maybe that is a drawing, but I think these are probably, they're two separate drawings. There's a faint division down the center, but I'm guessing they were done at the same scale. M107, I think is one. Notice that there's no concentration in the center of this. I mean, there's some bright, the darker spots in the center. And you know what? These don't appear to have condensed core. How far do I have to go back? I mean, look at the condensed core here in M13. And M13 is shown with that, and it's clearly in that photograph. But I think 107 does not have that concentration. Oh, this is a black and white photograph reversed from the Sky Center of Adam Block. So this is a good example because clearly that's got a really condensed core, and that's one of the qualities you may want to look for. A couple of books that I can't live without. This is the Messier Marathon by Harvard Pennington, who has since passed away. This is a stunning book, and this is where all my drawings came from. So star chart on the right, and then beautiful drawings of each of the objects. That's where my drawings of 37, 36, and 38 came from. You've already seen this. And here that business. This is a little tedious to read. I should have had 13 in here. So we saw 107, the last one that I showed you, diffuse and poorly concentrated. It's interesting because, yeah, I guess it's more diffuse, but it still looks pretty concentrated, but doesn't have that really bright center. That's why I put that in there. So anyhow, this book taught me to see. And then this comes from the talk and from the paper that I discovered years ago about learning to see. So you look at something, and it's funny, I remember trying to draw a lunar crater, and I drew a circle and I started filling it in. And then it says, is the object round or oval or irregular? And I realized that I had drawn it round and the crater was really oval. And that was illuminating. If not round, which direction? Is it brighter or less bright in the center? We've been talking about that. Is the brightness gradual or the gradient gradual or abrupt? And we're just talking about that. Are there any dark markings? And this is for anything you look at in the sky, not just clusters. Are there any dark markings? And we saw those dramatically in M13. What size is it compared to the known size of others? And once you calculate your field of view, you'll have a better sense of that. What's its magnitude compared to other magnitudes? Does it resemble any other known object? I think you'd probably need to, unless you have a brilliant memory, which I no longer have, you would need to make notes in a little notebook. I was going to sketch all the Messier objects and just make some notes. I think I did 3 of them before I realized it was overwhelming. But these are all things you can say to yourself at the eyepiece in hopes that you will discern more subtle things about the objects. The end.